This one, it ends up actually that it really doesn't matter if this is uniform or non-uniform if I'm trying to find the voltage right at the center. I'm going to show you in a couple of minutes how to do the voltage. If it's off center, then that will matter. Because if it's at the center, all the different pieces of the rod are equidistant from it, right? And if there's more charge here than here, it doesn't really matter whether it's uniform or there's more charge here, because voltages are a scalar. They don't, in other words, for electrical field, it mattered. If I want to find the electrical field here, it mattered whether or not this was uniform or not. That changed the voltage here. You see, so for electrical field, if it's uniform, so then you take a piece from here, you say, oh, okay, the electrical field they create is like this, then only this survives, right? That's the idea. And then as you're going to pieces that are more up here, then the electrical field they will create will be like this, and then that one will create like that. So those tend to cancel more. Their Y components cancel, and only their X components survive. So if it's non-uniform and there's more charge at the end, if there's more charge here and almost nothing here, and then more charge here, so I would expect these ones to cancel more because those ones already tend to cancel a lot. So these ones will create a very strong E field. But the unfortunate thing is their E fields will cancel more, right? And then these ones will create a weak E field. And they won't cancel, but since they're weak, the overall E field of this guy is going to be weaker. So E total here is going to be weaker than the E total there. But for voltage, it doesn't really matter because voltage is just a number. So if you have more charge here, but it's still equidistant from this, and then whether the charges are distributed uniformly or more charge here, it's just going to keep adding up. So we expect the same answer. So then what would the answer be? So then you have dV is equal to K dQ over R, integral, and then you have V is equal to, since the distance is equidistant, the R just comes out of the integral, and you have just K over R dQ. Right? So literally there's nothing to integrate. The reason why electric field there was something to integrate is because there was a cosine theta that we had to integrate. We had to worry about that, you see. So then this one ends up just being KQ over R. Okay, and then that's it. 9 times 10 to the 9th, 10 times 10 to the minus 9. Okay, and then R is going to be what? The R is going to be the radius of a circle with it'd be 6 meters. So that'll be what? 6 over pi, right? 6 over pi. This one cancels. 90 over 6 over pi. So whether it's uniform or non-uniform, it could even be that these charges are distributed asymmetrically, like most of them here. The voltage is kind of a weird thing because it's a scalar. It really doesn't matter as long as, hey, if it's equidistant, then the voltage shouldn't matter. Let's go see if these predictions that I'm saying are right. That trustworthy simulation is so good for all these things. That's probably one of the best simulations that I've seen. I'm just going to cancel that. At the center, okay. So the electrical field is 241, and then the voltage is 200. The voltage is 220 volts for uniform. So the voltage is 220, and then electric field is 237. I think it was okay, so we have electric field. So for the uniform, the electric field is 237, 220. Okay. Oh, and now let's find the voltage somewhere off here. So let's say, you know what, let me put the grid. Let's go 1 meter this way. Okay, so the electrical field 1 meter off to the side is 62.9. And then the voltage is 94 volts. Okay, so now if I make this rod non-uniform, let's see what's going to happen. So let's put more charges towards the end. Now what should happen to the electric field in the center? The center, I'm kind of taking it where the electrical field is straight, where it's horizontal. You see, right there. So now the electric field is 212. So what happened here? Does that make sense? More charge towards the end. Electric field went 212. Okay, how about 1 meter to the side? Was that affected? Ooh. Okay, how about voltage? Am I still on? It said my internet connection is off. Can you guys hear me?
Yeah, I can hear you.
Oh, okay, okay. So, okay, now let's check the voltage. 233. So this is volts per meter, 233 volts. And then 1 meter to the side, 96 volts. I kind of don't like that result. Eesh. So let's see. Here's the summary of that little experiment. So uniform charge in the center, I got electric field 237 volts per meter. Non-uniform, I got 212. Okay, that makes sense. I got smaller because there's more cancellation. right? How about the electrical field here? 62.9 volts per meter, 1 meter to the side. But this one is actually larger than that one. That's kind of weird. Does that make sense? What do you guys think? So in other words, here, the fact that there's more charge here, they're canceling more. So here the electrical field is weaker than this, but over there, the electrical field is stronger than this. The only thing I'm thinking of is maybe one argument that we can make is maybe this charge is so big, and then look how close it is to that spot, you see. Whereas here, the charge is uniformly distributed so that, oh yeah, this guy is close to there, but it's not very strong charge. So the charge is kind of distributed throughout. So as you're going farther away, the electrical field of this guy is getting weaker quicker, you see. Whereas this one, the electrical field maintains its strength for a while, but over here it's weak. So if we draw the electrical field lines, maybe I'm thinking the electrical field lines will look something like this. Here, the electrical field lines will look like this. And the same thing on the bottom, so it's symmetric. You see, here the electrical field lines will look like this. So I'm thinking here, it might be weaker than this guy. And see here, it might be weaker. This guy might be weaker than this guy. But over here, it might be stronger, you see? So just because over here the electrical field is weaker here doesn't mean here it has to be weaker. You can kind of, because what's happening is that the field lines are coming and there's a lot of charge here, so they're pushing on each other, so it's kind of not allowing them to penetrate that area, you see, as much. So they're pushing, but by the time they get to this area, they're still more concentrated than this one. Here it kind of goes like this, you see. So in other words, the electrical field here increases, and it increases faster than the electrical field here. I mean, it still drops, but it maintains its strength for longer than this guy. Okay. Now, so I can kind of see why the electrical field there was stronger than here, but here was weaker than here. But how about voltage? What had I told you that I expect the voltage to be? I said the voltage should be, if there's more charge here and here, it shouldn't matter. The voltage here should still be 220. So I'm disappointed in the app. This guy should be 220 volts. No, yikes. The only way I can explain that anomaly is, maybe I didn't place it right. Voltage should be the same here, but then the voltage here should be bigger for non-uniforms if there's more charge here, because these bigger charges are closer, you see? These bigger charges are closer to that area. Okay, so let's actually prove that. Here we go. Okay. Paper. So let's go back to our trustworthy. Oh, what was the voltage at the center we said? It was KQ over R, right? So for the center, it really didn't matter. It was just KQ over R, whether it was uniform or non-uniform. And the answer came out to be 47 volts. Right? Okay, how about, let's say the length of this is still 6 over pi. Okay, so let's say about 2 meters away on the side here. What should be the voltage for uniform? Let's do the uniform first. And then the voltage of the non-uniform. Okay, so then you take a piece from here, dq, and then you do that distance. Okay, so you have dV is equal to k dq over r, where this is r. So it's the distance from that piece to over there. So then I'm going to define this as theta, and this is going to be 180 minus theta. And this is going to be the radius of the circle. So the radius of the circle is 6 over pi. So then k dq is going to be lambda dx. Okay. Oh, the reason that this ends up being an integral is that as you go around the rod, different portions of the rod are different distances from that point. So the center ended up being not an integral. So because the distance was the same, you see. So you say then lambda dq is lambda dx, and r is going to be what? So I'm going to use the law of cosines. R is going to be the square root of r squared plus 2 squared. So the law of cosine says this squared is equal to this squared plus this squared minus 2 times this times that. 2 times this times that times cosine of 180 minus pi. So law of cosines. So this squared is this squared plus that squared minus 2 times this times cosine of that opposite angle. And then cosine of 180 minus theta is what? Cosine of A minus B is equal to cosine A cosine B plus sine A sine B, right? So cosine of A 180 minus theta is cosine of 180 cosine of theta plus sine of 180. Well, I'm not even going to do sine of 180 because that's 0. So that means cosine of 180 minus theta is negative cosine theta. So I prefer to call this guy theta because it's measured from the center of the rod going out to the end, to the element dq. So that's the main angle theta. Okay, so then this just going to be, then I could put k lambda dx over square root of, now I could put what r is, 6 over pi squared plus 4 minus, this is going to be 4 times r is going to be 6 over pi. Actually, this is going to be just positive cosine theta, right? So because the cosine of 180 minus theta was negative cosine theta, so that will switch that sign. And then this is 4, and then r is 6 over pi. Okay, then we can integrate that. Okay. So then what do we do? How do we integrate when we have a dx and a theta? So we do the same technique that we did for electric field of rod, right? This one be voltage K. If the lambda is uniform, it will come out of the the integral as a Q over L, right? The Q, the charge of the rod divided by the length of the rod, and then you're left with dx. Then dx is r d theta. It's the length of this thing, dx. So it's the same thing we did back in the electrical field chapter. Dx is r d theta. And then this whole thing, I'll just do a circle like that. And then the r comes out. And this is 9. This is 10. The length of the rod is pi r. Pi r, so the r's cancel, right? Pi r. So then the only thing left is just pi. Yeah. R, this is pi r. And then, so whatever the integral gives us, times this. Oh, then what are the limits of the integral? 0 to pi over 2, and then double it. So then I could double it. Then I go from 0 to pi over 2. Okay, here we go. Okay, so I have 6 divided by pi to the power 2 plus 4 plus 24 over pi times cosine x, close parentheses. So of course this view is better. You get to really see if you put it in right. So 6 over pi squared, 4 plus 24 over pi cosine x square root. That's it. So 0 to pi over 2. Okay, here we go. Okay, 0.45081. 45081. Okay. So then just multiply that by the, I'm doubling it. Then the 9 times the 10. Point 45081 times 90 times 2 divided by pi. Okay. 25.829 volts. Let's see. Well, it's in the ballpark. I can't really tell if it makes sense, but of course it's smaller than the voltage created by the by that same rod at the center. So yeah, definitely makes sense in that sense. Okay, now non-uniform. And what did I say? The non-uniform should be, if there's more charge here and there, should be bigger than this. So if we get something like 28, 29 volts for that, okay, then it's really making sense. So remember, the non-uniform at the center should still be 47 volts, but the voltage there should be higher. So maybe a couple volts more than that. So what's the difference between the non-uniform? At this stage, you put lambda is alpha x, right? I'm still using the same non-uniform that we had when the rod was straight. So we put alpha x, and then the alpha comes out. So you see, this part is different. The Q over the L, you don't have the Q over the L anymore. So let's just pick it up from here. Okay, alpha comes out. Then you have x. It was absolute value of x, right? Dx over, and then you got this whole thing in the bottom. So can I go? Oh, in this case, I could just go, since the charge distribution is the same here and here, I could just go 0, say x is r d theta, dx is r, no, say x is r theta, and then dx is r d theta, right? So in other words, not worry about the absolute value of x and then just double it. Because it's symmetric. So in other words, the distance of this side and the distance of that side is the same to that point. So I don't need to say, oh my God, I have to integrate the whole thing. I can just double it. So let's see here, where are we? 2k alpha x, so then say 0 to pi over 2, and then say x is r theta, dx is r d theta over square root of that whole thing. So then r squared comes out. So then you're going to have voltage is 2k. What was the alpha? I believe it was q over, was it q over 9? In one of my papers. Yeah, I think it's q, yeah, q over 9. So alpha was q over 9, and then r squared. Okay, so these and this comes out as an r squared. So then you have 0 to pi over 2 theta d theta over square root of that whole thing. Okay, here comes the moment of truth. Let's see. So go back to this. So you have an extra x up to the top, right? Or, sorry, because you have theta d theta. So the x is the theta, right? So x, I think that's it. Just put an extra x. Okay, so we're getting 0.37445, and then we'll just round that 1 to 4. Okay, so then, okay, so the integral came out 0.374454, and then what happens here? 2, 9, the charge is 10, this is 9, and then the radius is 6 over pi squared. And then the 9 and the 9 cancels. Okay, here we go. 0.374454 times, so then 6 squared, that's going to be 36, divided by pi squared, right? times 20. That's it. Times 20. Yes. Oh, wow. Oh my gosh, that's perfect. Yeah, the app was even, the simulation was even telling us that, right? Couple volts bigger than the volts of the uniform. Oh, wow. 27 volts. So, wow. Nice. Nice. So the uniform can always act as your basis of comparison then, in often cases. The uniform is a bit quicker to do. You don't have to worry about what the lambda is. You just say Q over L, right? But then once you have the integral of the uniform set up, the non-uniform would be easy to put, like theta something, theta squared or theta cubed, right? So then you can always compare it to the uniform and say, am I in the ballpark? Cool.